Hello, everybody. Welcome to our webinar today about Overland oil spills from pipelines. I would like to check the sound first before getting started. If you can use the chat window or the questions window, you can quickly send me a note just to make sure that you can hear me well. I will highly appreciate that. Okay. It seems you can hear me well. Okay, so we are very excited here to announce today the forthcoming release of the new OilPipeline tool for OilFlow2D. Excuse me. And I will show you sneak peek of that new tool today. We have been working on this for some time, and not continuously, but I think that the end result is quite useful for doing this type of simulation. So I hope you will appreciate that. So the webinar, I'll first do a very quick introduction to the OilFlow2D model for those of you who are not familiar with that. And then I will show the different steps that are required for what I call a mono application or a single application of the OilFlow2D model. Then I will show what I think are the main challenges that we normally face when we need to deal with multiple spills from pipelines. And then what are the characteristics of the OilPipeline tool that address some of those challenges. And then I will show you some examples at the end of the new tool. If you have any questions, of course, you can use the question panel to post the questions. And at the end, I will, if there are any questions, I will read them and for everybody and answer them so that, yeah, if you have any comment as well. First, some acknowledgement. Want to acknowledge the amazing team that we have, both in Spain office and University of Zaragoza, and also in our US office. These are the people that make all this development possible. And also, of course, the support from many clients that are continuously updating and making also possible that we continue development of new tools every year, and we highly appreciate that. Okay, so what is OilFlow2D? You may be aware that hydronic has two main areas: the environmental area and the flood analysis or hydrologic area. In the environmental area, the OilFlow2D is the main model, and RiverFlow2D, which is the main model for overland flooding or riverine analysis, also has a pollutant transport component that deals with dispersion of solutes or pollutants that can disperse in water. The OilFlow2D is a model that is dedicated to the analysis of spills from crude oils or oil-related fluids. And it has two main modules: the oil spills on land module and the oil spills on water modules. They are two independent now, and I stress now because in the future we are going to integrate so that we can have an integrated modeling of land spill that starts on land and eventually ends on water body. And we're also working on that, and we will have news, I think, very in the very near future, and I mean this year for that. So the oil spills on land model, as its name implied, it deals with spills on land when they originate on a tank spill or a pipeline or something terminal that spills initially on an area that is dry. And it can deal with various oil properties, so it can adapt to different fluids, different density, different viscosity, different yield stress, and it interacts with the complex terrain because it's the full two-dimensional equations, which means that when we say two-dimensional, it's sometimes people call this quasi three-dimensional because it actually deals with the three-dimensional terrain, but the characteristics of the oil, of the parameters that identify the oil, are not varying in the oil column, so they are uniform in the vertical within the oil. But the oil characteristics vary in space and time, as in a true two-dimensional model. And it has a component that we developed in the past couple of years, that is the heat transfer component. And the heat transfer is useful for situations where you have a fluid that may have a high pour point, like asphalt or any other fluid that can generate a high wax content, and in turn that can affect significantly the properties of the oil as it flows on the terrain surface. So the model computes for those situations velocity, depth, temperature, density, viscosity, and the yield stress for every cells within the mesh that it uses, the computational mesh. You can see an example here. Now, the oil spills on water, also, as its name says, it deals with spills that originate or enter the water at some point. And in this model, it's based on particle tracking, so it first needs to calculate the river or water body hydrodynamics. So that's the first stage, because the oil will move normally over the water body, and it needs to know the velocities of that river or lake. So based on that, the model uses a particle tracking method to determine the oil trajectories. And in doing so, it also accounts for the different processes that can occur within the oil that may affect its properties as well: evaporation, emulsification, dissolution, dispersion, shore interaction, and others as well. Now, all of the models are integrated in a graphical user interface. That is, the GUI is developed within the QGIS. QGIS is an open source geographical information system manager that you can use for many applications, but we have developed a plugin that allows you to work in the pre-processing and also the post-processing phases of the simulation. And the model also runs in standard CPUs, in standard computers, but it can make use of GPU or cloud computing if that's available to you. And that has also a significant advantage because it can run in parallel mode with thousands of processors, and that reduces computational time in a big way. Now, the heat transfer component has several characteristics and assumptions that are made. The oil temperature, density, and viscosity may vary in space and time. And again, this is an option that is available, but it's not necessary to run the model. You can take into account the wind speed, the air temperature, the relative humidity, the solar radiation. These are parameters that can affect the heat transfer between the oil and the environment, and also allows for options that determine how the oil properties depend on temperature. So by the model calculating the oil temperature based on the heat transfer processes, the model will also determine how the viscosity, density, and yield stress can vary for specific fluids. So the spills on land component can be used to determine the affected area caused by crude oil spills. In other words, answering where and when the oil will be in a given situation, and can assess if the oil is hitting high consequence zones, which means areas that are sensitive in some sense, depending on the if it's ecosystem that can be impacted or urban area. And it can deal with spills from well blowouts, pipelines, or tanks, and even multiple spills can and this was already in the model before the new tool was available. Now consider the dependence of yield stress, viscosity, and density on temperature. It is important sometimes, and depending on the fluid you have, but for high pour point fluids that can affect in a big way. It can completely change the way the model represents how the oil spreads on the surface of the water and also on land. Now, the workflow that was the only option that you had up to now to simulate multiple blowouts was to do it essentially one by one, or with multiple source component that I will delineate briefly. But essentially, you would need to, in the workflow, in the QGIS, you needed to create an OilFlow2D project that's very simple, load the terrain elevation, that's also straightforward. Then generating the mesh, that's also something that is, with the tools that are available, it's not complicated. The problem arrived when you had to assign the spill locations. First, you needed to assign the spill locations manually or in a kind of cumbersome way. But if you had few of them, that was easy. But if you had many of them, say hundreds or thousands of them, that was an issue. Then you would define initial conditions, set up parameters, run the model, and prepare maps and animations. Now, the running the model was we had the multiple sources, and if you have a pipeline divided in multiple spill locations, that could be performed in a batch mode that was available. But the preparation of maps and animations was something that was not automated completely. So you have to go one spill at a time. So if you have, let's say, 10, 30, 40, 50 spills, that wasn't a big of a problem. But if you have hundreds of or more spills, then that was very, very cumbersome or complicated. So the process of doing one by one is to use the QGIS. You would import the terrain elevations. Then you would enter a polygon that defines the limit of your area of interest. With this, you would enter, if you had a tank, as in this example, you would enter the tank boundary with the burst area here opening. Then you would, with that, you could generate the mesh. and the mesh would adapt to the irregular geometries, including the round structure in the weir that represents the tank. And then in this situation, where you would have an initial condition within the tank, that is the tank elevation, the tank oil elevation in the internal part. There will be dry conditions outside the tank. This is a detail of the lower part of this mesh that you can see is refined. So the mesh can adapt to irregular geometries. If you have buildings or any structure, it can adapt as much as you want by entering density lines or break lines that allow you to control how the mesh is generated. Now, at each point or at each cell, the model calculates the depth, velocity, and the other parameters as well. So it's important to understand that the more cells you have, the more detailed the results will have. And also, of course, the model will run slower. So if you have large meshes, it makes sense to use GPU because that reduces computer times significantly. Now, once you have the mesh, then you can enter the conditions. In this case, if you use the heat transfer model, you enter the environmental parameters, density, viscosity, yield stress that can also have their own loss to depending on the fluid you're dealing with. And then you select the oil spill on land module from here. If you use GPU or CPU, you can select it from here. Even the CPU is parallelized, so you can enter the number of cores that you have available and then run the model. And once the model finished, then you can process the results one by one. So you can see here, this is an animation that shows the difference in the oil trajectory and depth based on the wind speed. So with a high wind or a relatively low wind speed, you can see that for this particular oil, the run out distance from the originating tank that spills reaches much farther when you have less wind speed and less heat transfer in this case. These are other results that you can also see. In this case, we are animating the cell oil temperature for other conditions, and in this case the yield stress. You can see here that the yield stress is much higher for this situation, and the oil viscosity that is also much higher when you have more heat transfer. Okay, so that is available, it's still available, but that had the disadvantages that I have mentioned before, because when you had hundreds of spills to simulate for a risk analysis, let's say of a pipeline, that became a limitation. Now, to address that, we first looked at the challenges that this typical application have. First, normally in a risk assessment of a pipeline, you need to run hundreds, if not thousands of scenarios for long pipelines. Just so you have an idea, at least in the United States, the regulation called for approximately between 30 and 100 feet of separation between the spills for a risk assessment. That's about, let's say, 30 meters. So if you're looking at a long pipeline, Trans-Alaskan pipeline, for instance, would call for about 50,000 spills that you need to analyze. Now, for each spill, of course, you need to calculate where it goes, if it hits a high sensitive area, or determine the timing that it takes for the oil coming from the originating point of the burst until it ends its flow. But another problem that is, let's say, upstream from the spill itself is to know how much oil will come out of the pipeline, and you know, how long will it take to empty that section of the pipeline if that occurs. So you need to calculate the potential spill volumes, the flow rates, and outflow hydrograph for each spill location. And normally the spill location, when you do, if you need to do this for 50,000 spills, then you need to generate 50,000 outflow hydrographs. And each hydrograph, of course, is located at a different point, and they will have different hydraulic conditions within the pipeline when it bursts. So you need to know for these conditions, if this spill is located between two valves that will be closed as soon as it's detected. So you need to know the protocol of the pipeline operation. So at some point, if you have a spill here, you know that there is an upstream valve and a downstream valve that will be closed at a certain time. And knowing that information, then you will need to determine the outflow and how that discharge varies in time. So that's another challenge that we have there. Now, of course, once we have the outflow here, we need to do the simulation, and normally it's, you need to account for the complexity of the terrain that varies along the pipeline, as you can see in this typical photographs. And rarely you have one-dimensional flow because you have overland flow that goes anywhere. So you need to use a model that can handle that. Now, and then, of course, we have the characteristics of the viscous flow, that needs to adapt if it's non-Newtonian or Newtonian, and how the properties change. Oftentimes, the pipeline is heated to lower the viscosity of the oil and make it able to flow within the pipeline. But if the conditions, the environmental conditions or temperature is much lower than the heated temperature that you use in the pipeline, then as soon as the oil comes out of the pipeline, you will have an increase in the viscosity and the other parameters of the oil, and that can also affect how the oil behaves for a specific spill time. So once if you look at those challenges, I guess if you are looking at doing simulations, then the end result will be to generate maps. And if you have thousands of maps, then you need to have a way to automate that process and create the maps in the simplest way possible. So since each spill simulation generates a lot of results, they should be processed to create maps, and that that is something that needs to be also addressed. So these are the main challenges that we identified, and then for that we created the OilPipeline tool. Now the OilPipeline tool, it's an addition or a complement to the OilFlow2D model, and the initial release, as you will see, will have a relatively simple calculation method for the oil outflows that will be accurate, but we plan on releasing a full pipeline tool that not necessarily for use in spills, but to determine the operational aspects of the pipeline itself from the hydraulic point of view. So that's so the base of the OilPipeline tool is in fact a fully dynamic oil pipeline model that determines the pressure and the discharge along the pipeline based on the operational protocols that you may have. That means that the model can compute dynamically the pressures and velocities within the pipeline due to valve closures or any other typical operation of the pipeline. Now, the basic starting point of the pipeline use is the new oil pipelines layer. In the oil pipeline layer, you enter a polyline, and the polyline defines the geometrical characteristics of the pipeline. That means the XYZ of the profile of the pipeline, and or it could be also XY. I will tell you what we can do with the elevations as well, because the elevations can be taken from the digital elevation model if you don't have the actual profile with the elevations of the pipeline. And of course, diameter and other aspects and other data that we may need for the full pipeline tool will be the actual characteristics of the thickness of the pipeline or how it varies along its length. And then we have a new boundary condition layers for the pipeline, the OPL boundary conditions layer. That is the one that where you will have valves or the inflow, discharge, the pressure at the end, if that's a condition there. And that is used, this is used to determine the initial, mainly the initial condition of the pipeline, the initial pressure distribution, and also the general conditions of the pipeline prior to the spill. Now with that, then you can use what we have come to name the oilgram calculation tool. Now this word, I don't think it exists. We are calling that the oilgram, as we call the hydrograph. Then we are calling the hydrogram. Then we have the oilgram. We may change this name, but what we want to mean by this is this is the calculation tool that allows you to determine the outflow from each spill location. So first, we will create the spill points at specified intervals. Let's say if you want intervals every 30 meters, then or spills every 30 meters, then it will divide the pipeline every. You will put a spill location every 30 meters, and then calculate the outflow from each of those outflow locations. You will calculate a timetable of discharge versus time for each location based on the dynamics of the pipeline. And then it will create and populate the source layer. It will create automatically the source layer with all the sources. And the sources layer is the basic of the spills on land point model. And then once you have the results, is also the new pipeline tool allows you to automate the map creation for all spills. So instead of going one spill at a time as it was required before, now you can tell the model to create all the maps that are part of the spill analysis. Now, in terms of the workflow of the new oil pipeline tool, we have the same starting point. So from the QGIS, creating the project terrain elevations, that's not different, generate the mesh as required. Now the different part starts here. You load a pipeline and the boundary conditions for that pipeline, then calculate the oil grams or discharge versus time for creating the source layer. And then from that point on, it is the same as before, except that the preparation of maps is automated. So these are the difference between the new oil pipeline tool and the previous workflow. Now, in the new pipeline tool, once you have loaded the oil pipeline and the boundary conditions, you can use the new command that runs the oil pipeline break model, And in this oil pipeline break, you enter some data, how much, what's the simulation time, the report interval, the pipe, this is the time, the interval between spill locations that you enter, some information about the oil properties that is flowing through the pipeline, and some information about the internal conditions of the pipeline as well. Not all of these are necessary, because if you are not interested in the fully dynamic model within the pipeline, many of this information is ignored. For instance, fluid models of elasticity is only used when you are dealing with dynamic closing of valves, and that requires to know that parameter. But otherwise, it's not necessary. If you start from the initial steady state conditions, the data that you need is essentially the discharge, the initial discharge and pressure, and that's it. Now, in order to determine the elevation of each spill location, you can either use the elevation from the pipeline nodes if that's available, or to obtain the elevation from the digital elevation model. So if you are designing a pipeline and you may not have the elevations at each location, then you can use directly the DEM to that purpose. Now, of course, the pipeline may be overland or may be buried, and you can also adjust that if you want to accommodate that type of construction situation. So once you have that, you run the model, and that first step will be to it will create all the spill locations, as you can see here. And if you zoom in, you will see that you have, in this case, this particular pipeline has 747 spill locations that are separated every 100 feet. And so zooming in, you see more detail, and that's this separation is the one that I was referring to. Now, how do we determine the oil gram calculation or discharge versus time calculation? So we first determine the initial steady state based on the discharge and pressure of the pipeline. So knowing, let's say this is a schematic pipeline, we calculate the pressure along, or the pressures along the pipeline can vary along this given pipeline. Now, once we know that from the operational protocol, then for each slick point, or for each leak point that we have determined in the previous step, let's say we have a leak point here, what I call the rupture point R. Then we determine so the model will determine the profile, knowing the profile of the pipeline, the highest point to the left, that is PL, the highest point to the right, and it will, based on the continuity and the energy equation between the highest point here and the rupture point, and the highest point at the right and the rupture point, will compute dynamically, that means in an unsteady mode, how the pipeline is drained out through the rupture point. Of course, for that you need to enter additional data, that is the diameter. Maybe the rupture point is not complete on the pipeline, it's just a small diameter. You can enter that to determine the outflow conditions, but in general terms, the dynamic calculation based on the continuity and energy equations will determine a table of discharge versus time that is coming out of the pipeline at every given spill location. So when this calculation ends, you will have, for this particular example that I mentioned before, you will have 747 spills tables that are associated for each source that in turn will be used for the actual spill application. Now, this is just an example of a variation of discharge versus time for a specific point, and this is an output of the model. Now, since the model creates this this automatically, once you finish the creation of the spills, then you do the simulation. The simulation is also done in batch mode, so it's automated. So it will do all of the simulations in batch mode without user intervention at that point. And then at the end, you can also use the new tool to create all the maps that you want. You select which map you want, and then you can ask the model to create the maps for all of the sources. This is a new feature that wasn't available before. Now, this is an example that we did one of the tests that we have for, this is an actual pipeline, and this is a group of spills that have its own mesh. And so the spills for this particular group are generated in batch mode, as I mentioned. And then also once you generate the depth, you generate, in this case, we are generating depth for a group. And each group will behave independently. That means that once you have a group, then you will have for each source within this group the spill, and this is all organized in different folders. So when you do this kind of simulations, you have the results for each spill location. They are organized in a independent directory. So this is not all in the same folder. It's organized so that you can retrieve different result maps if needed afterwards. So let me, before just showing, so you have a sense of at least one part of the application of the model. I have here this pipeline that is the original pipeline is this one here, and I have the boundary conditions, which are valves that are defined here by these green points. Now the tool is it's simple to use. You just open the dialog here and enter the basic data. I will just enter here a simple just a distance to compute the and leave the default values. So this is the interval between spill locations. So this is the process. That's it. So once you click OK, the model will create the sources file automatically, and this is not pre-created. I'm just creating it now. So now we have all the spills, and each spill here has already a table associated with that contains the hydrographs. So everything is so if you look at here, so every point has the associated time versus discharge that is associated. This is a test case, but it gives you an idea of how fast the tool is to create the spills. Of course, once you have this in this situation, from this point on, it's the same as before. You run it in batch mode, and then you leave it for a few minutes. And actually, the case that I showed you before of a group, it takes 3 minutes to make the computation of about 20 spill locations for a 2-hour period. So it's not slow at all. Okay, so that's all I had to tell you. Just I want to mention that this tool will be released in in a forthcoming, probably during the month of March. And we are just testing different situations, different cases that we have to make sure everything works properly and smoothly. And yeah, you will probably receive an announcement of when is the final release is in a month or so. Okay, so let me see if I have any questions, and if you have any questions, you can use the panel to post if you want. Okay, I have a question here. If they ask if the model, this tool will be an additional module, or it will be something included for existing users. So yeah, for existing users that are current in the maintenance, as you know, the way OilFlow2D or Hydronia models work, if you're current in the maintenance, you get all the new tools. Even if it's a new model, you will get it for. In the case of OilFlow2D, any new tool will be available when the new release is done. So for new users, I guess that the dynamic model, the full dynamic model, will be an additional module that you need to acquire, because not everybody is interested in that, and burden the model with additional things at a higher cost. I don't think it makes sense. So it's better to put it as an option, so that the people who do not need it, are not necessarily needs to spend more money on that. Okay, I have another question here. What about multi-phase flow in pipelines? Well, that is not on our plans for now. At least for the dynamic model, we are going to deal with mono phase or single phase fluids. Going to multiple phase is something that we may look at that in the future, but it will depend on our analysis of requests from users that if we really see the need for developing that. We had a couple of compositional model in the past that we worked on, but we didn't work it for it's not a commercial type of model. It was a model developed for an old company, and it was for internal use, and also it has a compositional option and a let's say a black oil option as well. But at this point, the dynamic model will be single phase. Okay. So, yeah, I have a question in regards to the output of the model. What formats do we have in the model? Well, the same formats we offer up to now. All the maps can be generated in shape files or in raster formats. So if you want to generate maps in TIFF mode, the model can also automatically do that. So you can either select shape files or raster or both, and that's that will still be available here for the oil pipeline simulations as well. Yeah. Okay, I think that's it for now. So I just wanted to thank you all for your attendance and interest in our tools, and again, if you have any question in the future, or you have any interest in making any comment or request for future versions, feel free to do it. My email is ray@hydronia.com. and feel free to email me anytime, and I'll be happy to assist you. Well, thank you very much, and I'll see you in a future webinar.